So welcome to the next lesson in Level 2 Mechanics for NCEA, and we're going to look at the equations of motion, which we touched on in the previous lesson. So, how do we solve for finding the final velocity? We have an equation for that. Well, don't worry, we have the equation of acceleration equals the final velocity minus the initial velocity over time. So you can use algebraic rearrangement to give the desired equation. So the final velocity will equal the initial velocity plus the acceleration times time. So VI plus AT. But what happens if you want to know how far you've gone? Okay, so in a velocity time graph, how far you've gone is actually the area under the graph. So in this particular example here, the velocity is 80 meters per second, the time is 10 meters per second, and because we can rearrange the equation, the velocity equals distance over time to distance equals velocity times time, it'll be 80 times 10, or 800 meters. So graphs continue to give us more information. So the slope of a displacement time graph gives us the velocity, the slope of the velocity time graph gives us acceleration, and the area under the curve of a velocity time graph will give us the displacement. Okay, which is quite useful. So in this example here, how far have we gone? Well, in this example, we've got a triangle. So the area under the triangle is going to be the half the base times the height, or half the height times the base. Okay, so in this example here, the height can be, or half the height can be calculated by saying, well, I've got a final velocity, and if I add the initial velocity and divide it by 2, that will be half the height. Multiply that by the base time, and that will give us the actual distance or displacement. So in this particular example, the final velocity is 100, the initial velocity is 0, divide that by 2, so that will be 50 meters per second. Multiply that by the time, which is 8, so it'll be 400 meters. So we have a new equation. So what if you don't know the final velocity? Never fear, you can use the equation of the displacement equals the final velocity plus initial velocity times time divided by 2. But you can substitute the final velocity because we also know that the velocity or final velocity equals the initial velocity plus AT. Okay, so if you substitute that in, the displacement equals, or D equals VI plus AT plus VI, all in brackets, and then we can multiply that by the time and divide all that by 2. If you simplify that, I open up the brackets, it will be 2 VI times time plus the acceleration times time squared, or 2 VIT plus AT squared, divided by 2, and if you just clean that up, it will be the displacement, or D, equals the initial velocity, VI, times time plus half AT squared. So we have a new equation. And there's one final equation, which is the final velocity all squared equals the initial velocity all squared plus 2AD. Okay, so there's basically all our equations, which we've summarized here, or I've summarized here in a nice, pretty table. So if you know the initial velocity and you know the acceleration and time, you can find the final velocity by VF equals VI plus AT. If you don't know the final velocity, but you want to find the distance, you can use VI, or distance equals VI times T plus half AT squared. If you don't have the time, then you can find the final velocity using VF squared equals VI squared plus 2AD. And if you don't have the acceleration, you can use the distance equals the initial velocity plus the final velocity, or final velocity plus the initial velocity, times time divided by T. Okay, so it's important with these kind of kinematic equations that you know what variables are, or which ones you have, which ones are missing, so you can choose the correct equation. Okay, so just to finish off, we'll look at stroboscopic photographs. So in a stroboscopic photograph, a new snapshot is captured every number of seconds. Okay, so in this particular case, it's 0.04 seconds, and combined to show the motion over a period of time. So there's circle the part of the motion where the soccer ball is moving the fastest. That will be, of course, the point where there's the greatest distance between the different images of the soccer ball. Okay, so it'll be here, whereas the red circle is the part of the motion where the soccer ball is slowest in terms of its motion, which will be where all the soccer balls are kind of bunched together. It's not really traveling very far in those 0.04 seconds that the camera is taking its shots. So in terms of the stroboscopic photographs, that's quite a tongue twister. Is it constant velocity or is it accelerating? How do you know? Well, if it's constant velocity, then the distances between the balls, like on the top picture, will be the same distance apart. So it's going to be a constant velocity. And if it's accelerating, like on the falling objects on the right, or object on the right, then the distance between the photographic images of that one object as it moves down will be a greater distance apart, so showing it's accelerating.